Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and a very good day everyone. Hi, Dr. Zuhair here, and this is for the course of EPF3110 Mass and Energy Balance. Okay, in the previous topic I already described to you about different forms of energy. We have internal energy, we have kinetic energy and potential energy. So for this topic we are going to learn about the energy balance of the closed system. Okay, so we start with the total energy first. As what I mentioned before, the total energy is equals to the internal energy plus the kinetic energy plus the potential energy. Specifically for the closed system. Okay, again, as a refreshment, what does it mean by a closed system? Particularly from the perspective of energy balance. Okay, so a closed system, that means that the mass will be consistent inside without any changes during the process. So this is the mass. But in the same time, heat or work can penetrate in and out. Q1, Q2, W1, W2. This is what we call as the closed system. And in order for us to find the difference of the initial total energy with the final total energy, we also have to determine the difference between the internal energy, the kinetic energy and the potential energy of before versus after or final. Okay, so that we're going to get the changes of the energy throughout the whole process of the closed system. Okay, so for the closed system, I want to highlight the fact that we have two types of energy that we are going to measure. One is the total energy in the system, which is this, including the internal, the kinetic and potential energy, something related to the energy in the system. And in the same time, we also need to measure the total energy transferred to the system. Okay, so the total energy in the system here, and the total energy transferred to the system will be something that involve the heat or the work that go in and or go out from the system. So there are two types of energy that we have to consider in order for us to find the balance of this total energy. Okay, so energy can cross the boundary of a closed system in two forms. Okay, despite the fact that a closed system, the mass will remain, but energy can still cross the boundary of the closed system in two forms. One is heat and the other one is work. Okay, so we start with heat first. Heat means the form of energy that is transferred between the two systems by virtue of temperature difference. So in other words, if any temperature difference occurred, so heat will be going in or going out from the system. So in thermodynamics, this is what we call as a heat transfer. Okay, but in the same time, there is one condition where no heat transfer happen, and for this type of process we call it adiabatic process. So you have to be cautious about this term. If the question or any type of situation mention that the process is an adiabatic process, that means that no heat can transfer inside of the system. So it's really well insulated. No heat can transfer despite the temperature difference whatsoever. No heat can be transferred. Okay, and this adiabatic process means the system is well insulated, so the negligible amount of heat passes through the boundary, or both the system and surrounding are at the same temperature, and therefore no driving force for the heat. Okay, so that means if the system, let's say the temperature is the same for around, this is 30 degrees C, inside auto 30 degrees C, so this is also can be considered as an adiabatic system, the adiabatic process, because no temperature difference occurred, so no heat, no temperature difference, so no heat transfer. Okay, so that's the basic thing about the heat and the adiabatic process. And for the heat transfer, the the symbol is Q, but when it's come to the heat transfer per unit mass of a system, okay, so this is what we call as a specific heat, because we have to divide by the unit mass. Okay, so you can see here the heat transfer, the symbol is the capital Q, but when it comes to the specific heat, the symbol will be in the small letter Q, and it divide by the mass. And for the heat, the unit is kilojoule or joule or kilojoule, and now this for the specific heat is already changed to kilojoule per kg, because it is with the mass. And this is something related to the kinetic energy and the potential energy, in which if it's stated specific kinetic energy or specific potential energy, is something to do with the unit of mass and the rate of heat transfer. So this is, I'm going to put a dot here, sorry, a dot here, the rate, something to do with times. So when it's come with time, it will have this unit, kilojoule per second, or kilowatt. This is the unit for the rate of heat transfer, where the Q will be divided with time. So kJ, kilojoule, will be divided by second. So that's about the heat. Now we move to the other. Okay, so we have two. One is heat, another one is work. This is the energy that can be transferred in or transferred out from the closed system. Okay, so for work, with the symbol of W, if the energy crossing the boundary of a closed system is not heat, it must be work. Okay, if nothing to do with the temperature different, it will be something to do with work. Okay, work in unit, also unit kilojoule. So all the energy, regardless whether it's a total energy or the kinetic potential, even the Q and also work, all will be represented by the unit of joule or kilojoule. Okay, energy transfer associated with a force acting through a distance. So the keyword is a force acting through a distance. Okay, so work done per unit mass. Okay, so this specific work, just going to put specific work here with a small capital of W. That means the work will have to divide with mass, so that the unit will be kilojoule per kg. And then again, for work done per unit time or rate, work rate, the rate of work, with the symbol of W with a dot on the top, will have the unit of kilojoule per second or in kilowatt. So you now learn about the Q and also W, which is these two are the energy that is not from the system, the energy that transfer in or out of the system. Okay, so again, I would like to remind here, now we have two. One is the total energy, this is this, and then the total energy transferred on, which is the Q and W. In terms of the transfer of the energy, this is related to the heat as well as the work. We need to bear in mind whether it is going in or going out from the system, because this is very important for us to know whether it's going to have a positive value or the negative value, because it will involve with the calculation. We start with first with the heat. Okay, as the definition, heat energy that flow as a result of temperature difference between system and surrounding. Yeah, so the direction of flow is always from a higher temperature to a lower one. Okay, so imagine this is a system. Okay, so if the heat is transferred to a system, this heat is considered having a positive value. However, if the system transfer the heat to outside of the system, which is the surrounding, this Q is in the negative value, because this is losing the energy while this is gaining energy. Okay, so for work also the same, energy that flow in response to any driving force other than temperature different, such as force or torque or voltage. Okay, so if the work done on a system, okay, for instance, like this is a system. Okay, so maybe we include some electric in, so this is considered as work that going into the system. This is a positive value of work. However, if suddenly maybe because of the interaction of the molecule in the system is going to produce some pressure that push the boundary, and then maybe this is like a piston, where the piston go moving upward, there's some mechanical thing happen, and work had been released out, the system has produced some work out, and this is we consider as the negative value of work. In a simple word, something that when the process or the system gaining energy, regardless whether in terms of the heat of the work, this is all in the positive value. But if you are losing the energy from the system in terms of the heat or work, this considered as the negative value, and you need to understand this. And when you find any question related to the energy, particularly involving the heat and work, you need to define whether the system is gaining the energy or the system is losing the energy, in order for you to determine whether it's positive or negative value. Okay, so the similarity between the heat and work, okay, both are recognized at the boundary of a system as they cross the boundary phenomena. Okay, system possess energy, okay, but not heat or work. Okay, so both heat and work is energy. Actually, they are energy, and we consider the energy, not the heat or the work. Okay, both associated with a process, not state. State is stagnant, but a process, that's mean that it will have an initial value and the final value, so it's a process. Okay, from state 1 to state 2, it's not just going to be stagnant. The system is going to be in just a state. Okay, and both are path function. Magnitude depends on the path followed during a process as well as the end state. Okay, so we have the end state and the initial state. So when it's come to the energy balance on the closed system, as we know that no mass is transferred across the system boundary while the process is taking place. This is for the closed system. This is a closed system. The energy balance equation will be like this. Accumulation equals to input minus output. Input minus output. Okay. Well, actually, it's initially was stated like this. Input equals to accumulation plus output. But now we want to put the input and output in the same side. So we have the accumulation equals to input minus the output. So the input minus the output, we need to detail this general equation into the final system energy with the initial system energy. Okay, what is the initial? What is the total final energy? Final total energy, and this is equal to the net energy transferred to the system. Okay, still remember this is something related to delta E, and this is about the Q and W. That is the energy transferred to or the system to or to into or to out the system. Okay, so if we measure, so this is related to, okay, so in order for us to measure the total energy, so this is the total energy from in the system. Okay, so here we have the U plus P E plus KE, potential energy plus kinetic energy, in which if we want to find the difference of the total energy, we need to measure the difference between all of this energy, the final and also during the initial, and it's equal to Q minus W. Okay, because the reason why we minus W, because most of the time the work will be going out from the system, not into the system. So that's why we can to like simplify Q minus W. So we do the calculation. So at the end, we are going to get delta U plus delta EK, which is the potential energy, plus delta potential kinetic energy and potential energy is equals to Q minus W. And this is for the closed system energy balance. So this is the thing that you need to uh, understand and remember, and you need to find all of this energy first before you can have the energy balance of any specific system or process. Okay, so we have the final equation, the energy balance equation. That's something you need to remember, and this is again referring to the first law of thermodynamics for a closed system. Okay, in term represent the respective net cumulative amount of energy over the time interval T1 minus T2, not the energy per unit time. So that's mean that it is about the final minus initial. The energy of the final minus the energy of the initial, not the energy per unit time on the specific time. Okay, so there are few assumptions here when you want to do the energy balance equation, particularly for the closed system. Okay, first one, the internal energy of a system depends almost entirely on the chemical composition, state of aggregation, and temperature of the system material. So, if no temperature changes, phase changes, or chemical reaction occur in a closed system, and if pressure changes are less than a few atmosphere, then we can consider that the internal energy difference will be zero. So this is another assumption that we need to also remember. Okay, when we do some calculation related to the energy balance, we need to analyze the situation, whether the situation have some changes in terms of temperature, phase changes, or chemical reaction. If no changes happen, then we can consider that the internal energy difference will equals to zero. And this is number one. Point number two, if a system is not accelerating, it's not moving, then the kinetic energy will be zero. Okay, so the keyword is accelerating or moving. If a system is not rising or falling, then the potential energy will be zero. Okay, so when you have an equation related to energy balance, you need to first really read the question carefully and analyze whether the potential energy, the kinetic energy, and the internal energy, whether it is zero or not. Okay, depending based on all of these conditions. Okay, if a system and its surrounding are the same temperature, okay, or the system is perfectly insulated or known as the adiabatic system, then we can consider that the heat is equals to zero. Okay, so it's if the system if the temperature is the same with the surrounding and it's insulated, then we can consider that no Q involved in the energy balance. And lastly, work done on or by a closed system is accomplished by movement of the system boundary. Movement, okay, the keyword movement of the system boundary against a resisting force or the passage of an electrical current or radiation across the system boundary. So no movement against the resisting force, then no moving parts or electrical current in the system, then we can consider that the work is equals to 0. Okay, so these are the 4 criteria that we need to analyze first before we can do the energy balance, any type of energy balance in any type of process or situation. Okay, so let's just try example 14.1. I'm going to read the question first. Okay, a gas is contained in a cylinder fitted with a movable piston. So this is a cylinder with a movable piston. Okay, the initial gas temperature is 25 degrees C. Okay, so inside we have gas that have initial temperature of 25 degrees C. The cylinder is placed in a boiling water with the piston held in a fixed position. Okay, first the piston is fixed with a clamp here. Heat in the amount of 2 kilocalorie is transferred to the gas, which equilibrate at 100 degrees C. So the boiling water increased the temperature, so some heat had passed into the system, which from 25 it's now changed to 100 degrees C and a higher pressure. The piston, okay, so after it's increased to 100 degrees C, the clamp had been removed, and because of that, the gas does 100 joule of work in moving the piston. So the piston been moved because of the work of 100 joule to a new equilibrium position. The final gas temperature is still 100 degrees C. Write the energy balance equation for each of these two stages of the process. So we have two stages. One is the heating of the cylinder by the boiling water. Another one is the moving of the piston. Okay, and in each case, solve the unknown energy term in the equation. In solving this problem, consider the gas in the cylinder to be the system. So the gas is considered as a system. Neglect the change in potential energy of the gas as the piston move vertically. So although the position of the piston happen, but the question asks to neglect the potential energy of it and assume the gas behave ideally. Express all energy in joules. So what we need to do, we have to condition, okay? One, let me just draw it first. Okay, so this is the cylinder and this is the piston. So one is from 25 degrees C gas. We heat it up to be, I'm so sorry, my drawing is not really great, 100 degrees C. Okay, but the piston had been clamped, so the piston haven't moved. So this is the stage 1. Okay, stage 2 is when the piston with the gas of 100 degrees C, now they remove the clamp. It kind of like push the piston upward, so some movement happen. So this push like this, but the gas is still 100 degrees C here. So we need to find the total energy for the energy balance for these two stages. for these two stages. We start first with the stage 1 first. Okay, stage 1. That's mean the heating part. Okay, so let us first list down the energy balance. Okay, we have U plus KE plus PE equals to Q plus W. Okay, in terms of the symbol here, it's plus or minus. Well, actually depends whether it's from the system or it's out from the system. So we will see it based on the context of this question, okay, later. Okay, for this one, for this stage 1, let's just start with the potential energy first. The internal energy first. The internal energy means that when temperature changes or any chemical reaction happen, we can consider that there is some changes in terms of the delta U. Okay, so we have this. We need to find what is this. What about the kinetic energy? Any movement? Any from this condition, one, the initial to the final, any movement? There's no movement, so we can assume that the kinetic energy is 0. What about the potential energy? Any changes in terms of the position? No. So this is can be considered as 0 too. And then we have the heat amount of 2. So we have this as 2 kilocalorie. And then do we have any work happen here? So we go back here. No moving parts, no electrical current. So for stage 1, the work is also considered as 0. So at the end, we only have U. Sorry. U equals to Q. Okay, so we have Q, which is in, because all energy need to be expressed in joules. So 2 kilocalorie, which is the Q, we need to do some conversion of the unit. And kilocalorie, that means that is 1 power of 3 calorie per kcal. And then we change the 1 joule is equals to 0.2390 calorie. This is something that you can refer to your conversion table. So at the end, we are going to get, okay, sorry, this is all delta, okay, because we are measuring the difference between the initial and the final. Okay, so it should have the delta here. So we have the delta U equals to 8370 joule. So this is the answer for stage 1. Okay, so we only have Q and delta U. What about stage 2? Let's just go to stage 2. I'm going to change to other color. Okay, stage 2. For stage 2, you can see here, now the piston have been moved upward. Yeah, so let's just try to list down the energy balance first. Delta U plus delta KE plus delta PE equals to Q plus W. Okay, so we need to see one by one. Okay, for delta U, whether any changes in terms of the temperature. Okay, here we go to the definition. So no temperature changes, no phase changes. It's not stated that the water had been, so it's not water even, it's a gas. So phase changes and no chemical reaction happen. So for stage 2 here, we can consider that the delta U is equals to 0. Okay, what about the kinetic energy, the delta KE? The system is stationary at the initial and the final stage. It's not related to the piston, but the system itself is not moving. Okay, so we can also consider, so you have to you have to differentiate within the system itself with the boundary that have been pushed up. Yeah, so for the system itself, the kinetic energy is equals to 0. What about the potential energy? Okay, so we have here, consider the gas in the cylinder to be system, neglect the change in potential energy. So it's already stated here, neglect the change in the potential energy of the gas at the piston move. Well, actually, if the system have some position change, then potential energy might occur. But since this question asks us to neglect the potential energy, so we just going to assume that this equals to 0. So now we have 0 equals to Q plus W. Okay. And then we have stated here that the work is equals to 100 joule. Okay, so now the question whether the work is in the positive or negative value, because this work is from the system, it's not outside from this is from the system to the surrounding. This is not going in, but this is going out, where energy had been released out, not energy had been coming in. So we can consider that W here is equals to negative 100 joule, because it's going out from the system. So now we can have that Q is equals to 100 joule at the end for stage 2. So for stage 1, we have delta U equals to 8370 joule, and for stage 2, we found that the Q is 100 joule. So there's some example related to the energy balance. We will discuss a little bit further during the tutorial session. And I think the most tricky part is to understand where we can assume that all of this energy can be considered, whether it is 0 or it's contain or it has any value. So that's something that we will have to do a lot of exercises and see a lot of example in order for us to understand the concept behind it. So that's about the energy balance for the closed system, and we'll see you again in the next topic. Bye bye. Assalamualaikum.